Okay, let's finish up our look at the nucleophilic substitution reactions for now by having a closer look at the things that affect the rate of these reactions and the rate considerations. So the rate of a nucleophilic substitution reaction depends on the mechanism, so whether it is SN1 or SN2, the nature of the leaving group, i.e. how easily the halogen carbon bond is cleaved, and the choice of solvent, as we talked about earlier. So let's put these all together. The effect of the mechanism basically looks at whichever one is faster, SN1 or SN2. Experimental data has shown that SN1 reactions proceed more quickly than SN2. This means that halogenoalkanes will react faster than primary halogenoalkanes in a substitution reaction. Because secondary shows evidence of both mechanisms, their rate is somewhere in between. So we can place the relative reactivity of these three classes according to their mechanism as tertiary, being pure SN1 being the fastest, secondary because it is a mix of both coming in the middle, and then primary halogenoalkanes because they react via an SN2 being the slowest reaction for these types of substitutions. Okay, so SN1 with the formation of the carbocation from our tertiary halogenoalkanes is going to be the fastest reacting of these types of reactions. With the second one, the nature of the leaving group is critical, and this is one that students often make some mistakes in when they answer in the exams. There are two opposing things to consider with this. One is the polarity of the carbon-hydrogen bond, that being whether or not it's a fluorine, fluoroalkane, chloroalkane, bromo, or iodoalkane. The more electronegative the halogen, the more electron deficient the carbon is, therefore the more vulnerable it is to attack. With this also, we need to consider the strength of the carbon-halogen bond. The strength of the bond between carbon and iodine is greater. Okay, so, the reactivity is going to be greater for iodine through to fluorine. So if we look at the bond energies, which you have in your data booklet, you can see that the strength of the carbon-halogen bond decreases from fluorine to iodine. This means that we see the opposite trend for the strength of the bonds than what we saw for polarity. The more polar bonds actually have a stronger bond to the carbon. This means that one can have a greater influence over the other, and experimental data has shown that the strength of the bond is more influential to the rate than the polarity of the bond. Often we will see that students mix this up, but it is important for you to remember that the relative rate of reaction for the halogenoalkanes is then based on the strength of that bond, and the strength of that bond typically has to do with the size of the halogen. If you think about iodine, it's got a very large atomic radius, so we have the carbon here, and the internuclear distance between these two is going to be strained. That bond length is going to be quite long because of the repulsion of the electron clouds. So the strength of this bond with the larger halogens is weaker, which means that it is easier for it to cleave, forming the leaving group. So the rate will go in order of an iodoalkane will be faster than a bromo, which is faster than a chloro, and faster than a fluoro, okay, even though the polarity is the opposite direction. The last thing that can influence our rate is the choice of solvent. And we talked about this in the previous video where we said that SN1 reactions are favored by polar protic solvents, SN2 are favored by polar aprotic solvents. So choosing the correct solvent will speed up the rate of reaction for both mechanisms. If we use the wrong solvent, that will compete and slow down the reaction. The fastest nucleophilic substitution reaction would occur with tertiary iodoalkanes in a polar protic solvent. In general, when we look at the nucleophiles, a stronger nucleophile will carry a formal negative charge. So OH- is going to be a stronger nucleophile than water or alcohol. OH- is negatively charged, so it has a greater affinity for the positive charge on the carbon. We get partial positive or the formal charge of the carbocation. It's less electronegative, so ammonia is going to be a better nucleophile than water because the lone pair on the nitrogen is going to be more easily donated in order to form that dative bond when we start the actual substitution process. Okay, so ammonia will be a better nucleophile because it's less electronegative than water. So if we're talking covalent uncharged compounds, the less electronegative atom holding the lone pair will be the better nucleophile because the atom is holding the electron pair less tightly, so the dative bond is more readily formed. This diagram gives us a summary of SN1, SN2, and I strongly encourage you to form a mind map or a revision sheet comparing and contrasting SN1 and SN2 and practice drawing the structures for the reaction mechanisms because you need to be able to often draw these using curly arrow notation in your exam questions. And I'll see you in class.